the stream here. So you may have noticed I gave you a present. You have no homework due this week. I have pushed it back. I had the room in the schedule, so I decided to do it. So you have, I just put it up today, homework 4, which will be due 3:15, so that's a week and a half or so. You have a quiz that will be due on Tuesday, and note that it's right here. It is a worksheet that I want you to fill in. I couldn't figure out how to make that work on Canvas, but we can take a look at that real quick so I can try to describe what I'm looking for. So this is a drill on notation. So I have 4 different models across the top here. I want you to figure out, based on the notation, what are the fixed effects, which terms represent level 2 variances, and which terms represent level 1 variances. So you're going to write in the box the things that correspond to each. And note that I say, and their interpretations. So like if you find that you have random intercept variance goes in one of the boxes, what does that mean conceptually in that model? If you had to define it with words, what would you say? So this is just a drill to make sure that we're following notation. As usual, the point of these quizzes is to make sure that we're reviewing the right stuff and that you're taking away the right stuff, so you should do it off the top of your head. Try that first. If you find yourself struggling, then you'll know what to look back to. So that's the idea, and then we'll go over the answers together as usual. So that will be due a week from today. So let's see, what else do we have? I think that's all the logistical things. Any questions? No? We're ready to dive back into some linear models, multi-level linear models. By the way, I am going to be teaching the clustered data version of this same course in the fall. So you'd all be welcome to join me. Spread the word. I'll be sending out announcements. So I'll give you a hint. It's exactly what I'm saying, except I'm going to put IJ instead of TI, and it'll be between and within groups instead of between and within people. So you'll have an advantage because you've already heard it one time. So I used to try to teach a 5-day workshop for ICPSR where it was 8 hours a day for 5 days, and they wanted me to do both in 1 week, and it was nearly impossible because like what level 2 meant on Tuesday was different than what level 2 meant on Wednesday, and it was just like hard. So I keep them separate, and that's the decision that I make. But we can do some reviewing. Would that be good? Okay, so we're talking about modeling with in-person change. So studies where it's over time and time is on purpose, collected far enough apart in time so that people are showing change. And so we went through a series of models where we're building up from the smallest possible model into something that's supposed to look more like the data. So this is our starting point here. So change in notation, just to review the multi-level notation. So level 1 model is the time-specific outcome for each person. So it's per T per I for time and individual. Time is level 1, individual is level 2. It is a function of a person-specific intercept placeholder. So beta 0I is not a parameter that's estimated. It holds estimated parameters at level 2. So beta 0I is how each person gets their own intercept. It starts with the fixed intercept, this gamma 0, 0, which is the average intercept. So you can think of it as the grand mean of the person means. From there, we have the random intercept deviation for person I. So it's how far off you are. So you can think of this as one distribution where the mean is the fixed effect and the variability around it is described by this U0 term for each person. So we estimate the variance across these U0s as the model parameter. After we give each person their own intercept, we stick that back here in level 1 and we pick up E, which is then how far off you are at that occasion from your own mean. So putting it all together, 3 terms. So no matter what kind of longitudinal data, we start here. So this model isn't a model that's expected to fit well. It is used pretty much exclusively for one purpose, which is to calculate the intraclass correlation. So that then, the model for the variance for this would look like this, where we have the total data put back together again is V, is a function of the between persons part, level 2, That's the ZG, Z transpose, that part. And in this case, Z is a matrix that holds predictors that have random effects. So this only random term right now is intercept, which is why it's column of ones. Use zero variance right here in G. We then, after doing that multiplication, can add it straight to R, which is your level 1 variance. This model says that the E's have constant variance with no covariance. That's an assumption that we can check and modify as needed, which gives us this compound symmetry structure, where equal variance across time, equal covariance across time. When you translate that covariance into a correlation, it becomes ICC. So this tells you then how much of the total variability is at level, say it with me, 2, yes. How much is between? How much is due to cross-sectional mean differences? So what ICC means game over? What value of an ICC means stop? You do not have longitudinal data. 0 or 1? If the ICC is the proportion that's between, what value of ICC would say you don't have any longitudinal information? It's 1. All between, all cross-sectional. So that would mean even though you measured people repeatedly, they told you the exact same thing every single time. So long as your intraclass correlation is under 1, you're good to go. So then we talked about adding the effect of time. And in particular, there's 2 distinct types of effects of time. We're talking just linear to get started, but then we'll quickly get into more nonlinear forms. Fixed effect is what happens on average, the part that's constant for everybody. Do the means change over time? That's a fixed effect of time. In addition to that, we can ask whether each person needs a different effect of time, where there are individual differences in change. And if so, then we also need a random effect of time, meaning each person gets their own. So then we looked at these figures here. So top left, no change on average, and everybody no change is the same. So there's neither a fixed effect of time that we would need in the model, nor a random effect. Everybody no changing the same is why there's no random effect of time. There is a random intercept in all of these pictures, though. People start out at different places. Top right, yes, there's a fixed effect on average. The black line here, the heavy line, people are growing, but everybody's growing at the same rate. These are the only 2 pictures in which a random intercept-only model would be sufficient. These are the only 2 pictures in which repeated measures ANOVA would be fine, in which compound symmetry holds. The variance stays the same across time if everybody changes the same. Bottom 2 pictures then include a random effect of time where people change differently. And that can be around a 0 fixed effect of time, meaning there's no significant fixed effect, or it can be in addition to there being a significant fixed effect. Either way, when we're building models, we keep the fixed effect of time in before adding the random effect. The random effects are always phrased as how far off you are from the fixed effect. So the fixed effect is the reference point. It has to stay for it to make sense. So practically speaking, that also means if you were to add a fixed effect of time and find it to be non-significant, doesn't mean you have to stop. You can go ahead and test the random effect too. That would give you the picture on the bottom left here if it were significant. You can have no change on average because some people go up and some people go down. That's possible. Okay. So then we looked at a model adding a fixed effect of time, where we pick up 2 placeholders, beta and level 1, how each person gets their own intercept, how each person gets their own slope. Because there's 2 beta placeholders in level 1, there's 2 level 2 equations. At this point so far, beta 1 is defined only by a fixed slope. Everybody shares the same slope. Everybody grows the same. In adding that fixed effect of time, So you can see it more clearly with the bottom composite equation where you take out the beta placeholders. That fixed effective time explains variability. So this is a really important distinction in terms of model building. When you're adding terms, what they're for. When you add random effects, you're not explaining anything. You're partitioning variance into different kinds, but it's all still error. When you add fixed effects, now we're explaining variance, and that means some of your variances should go down. Which ones, or which one, depends on the level at which your predictor variable is measured. So time is measured at level 1. Therefore, when you put in a fixed effective time, it explains level 1 variance. When that happens, because of the way level 2 variance is estimated, it's going to go up. It's not a problem, it's just a consequence.
I got one question.
Sure.
For the level 1 covariance, does it matter whether it's time varying or time non-varying?
Yes. So time is a time varying predictor, right? Anything that's measured at each occasion goes in the model as a level 1 predictor. Anything that is measured only once, or anything that is an aggregate over time, that goes in the level 2 model instead. So yes, it matters in terms of notation. Conceptually, it matters as well. The job of a predictor in the level 2 model is to explain level 2 variances. The job of the predictor in the level 1 model is to explain level 1 variances. Okay. So we talked about that, talked about that, compound symmetry, constant variance, and I think that's about where we left off when we were ready to add random linear time. So we did this at the end, so we'll go back to that. So now next step, after adding a fixed effective time, I'm on slide 19, we're adding a random effective time, U0I. So U0I is how far off your slope is from the fixed slope. Because U0 and UI relate to the same person, even though it's not shown here in the scalar equations, you're also going to add a covariance between them, and that's going to show up in G. So then here's a picture that may help explain what each of these terms is doing. So in the picture, time is on the x-axis. I have centered it such that 0 is the first occasion. That way my intercept has a meaningful interpretation. The black line is the line through the sample means, so overall across everybody. The blue line is for one particular individual. We've got 4 occasions. So starting at the top here, gamma 0, 0, the fixed intercept. Given that we have time in the model as a predictor, the intercept is specifically when all the predictors equal 0, which is time 0. So in the picture, that's 10. Now note that the actual data point is not 10, it's a little below it. What the intercept refers to is the predicted mean by the model. The model is the line. So you hope it's as close to the data as possible, but it's not going to be exactly the mean at time 0. My blue person at time 0 is lower than everybody else. So their U0 is a -4. If you put 10 with -4, you get to the person's predicted intercept of 6. And again, same idea, it's not exactly that person's time 0 value. It's their time 0 value predicted by their model, which is their own line in this case. Then we have our fixed slope. That's the slope of the black line. Rise over run, as we learned in algebra in like junior high, remember that? Delta y, delta x, that was the other version. So that's 6. On average, for every 1 unit difference in time, the mean goes up by 6 for the sample. But my blue person they're changing more quickly than everybody else. So their random slope would be a positive 2 to get them to their actual slope of the blue line, which is 8. How far off? Then last but not least, so long as you have 3 or more occasions, those lines aren't going to fit the individual data perfectly. So what's left is E. So there would be 4 E's in this picture. I've only drawn 1. But here, the actual outcome is lower than the line thought it should be, so it's negative. Here, it would be positive. Here, it would be about 0, and here it would be negative. So E variance then is time-specific variance that's unrelated to how people change. Said more easily, E is why are you off your line today? What's going on at time 4, here, or the last occasion, that made you lower than the model thought you were going to be? Did your baby keep you up all night? Are you stressed because of comps? Right? Something transient, something acute, right? Hypothetically, right?
Both of them works for me. Both of them works for me.
Yes, yeah. But point being, it's something acute, something specific. Beyond just the fact that you're on your own trajectory that's different than everyone else, why are you off your line today? That's E. So if you think about this fixed and random, it is possible to get the model to predict the U's for you that for each person, but we typically don't do that. But just to give you a sense of how this works, do this here, fixed and random. I'm giving you values, make this big. So what if I had this combination okay? First case, if this was the combination for your person, I would describe that person as growing more than average. Their random slope is 2 units more positive than the fixed slope of 10. Next one. The random effect is negative. Does that mean they're declining? No. How would you phrase that?
So they're still growing, but slower than the average.
Yep, they're still growing, but slower than average. So I'm going to put some words up here. I would call this trajectory more positive. This one, I'd say less positive. Still growing, but just less. How about this one? Is this person going up or down? Going down. Relative to everyone else, though, less down, right? Yes, less negative. And how about this person? More negative, declining more down. Pick your set. Can you tell I aced the GRE verbal section? More down. Look it up, it's in there. More negative. There. This pattern, by the way, is going to recur in a lot of different examples. You can think of this as only 4 kinds of interaction terms in the world, or nonlinear effects in the world. Things can go either more or less positive or negative. So this shows up very frequently in describing what happens for in models where effects are linear combinations. All right, with me? Okay, cool. So what's next? So the idea of unbalanced time then. Unbalanced means people are on their own measurement schedules. So let's say that you have this trajectory for your sample. You're measuring infants. 3 weeks, 6 weeks, 9 weeks, 12 weeks. That's the trajectory for the sample. Let's say that one of your babies comes in at 3 weeks, does fine. They come back at 6 weeks, and then their parents stop returning your calls. That's all you get. Fine. I would call these data balanced, but incomplete. They came when they were supposed to, but they're missing the last 2 occasions. In contrast, you might have a pattern where somebody comes in at 3 weeks, but then their baby was sick and they couldn't make it until week 7, and the same thing happened at week 11, and then they showed up when they were supposed to. So the best fit trajectory through their means to the best of my PowerPoint ability here would look like that. But what if I thought I had to stick to the time schedule that I had intended? What if I were fitting like an ANOVA model where the only option is saturated means, time is discrete? Well, if I move time 2 over here and time 3 over here, what happens to my line? It's different. By rounding time, you're introducing measurement error. You don't have to do it. So this is what I would call complete data that's unbalanced. I've got 4 occasions. They're just not the 4 I had intended. That's more common than not when you're dealing with real people in the real world. The other thing to keep in mind, though, a consequence of trying to infer what the slope would be for each person, this person's slope down here that's based on only 2 points, it's less reliable. So we don't trust it as much. If I were to ask the model to predict its best guess for what the slope, random slope would be for each person, that person's slope is going to get pushed to look more like the average. So this happens whenever you have individuals who have less data or their slopes look way different than everyone else's. The term for that is shrinkage. That's one of the reasons why we don't need or don't want to estimate the slopes for each person. All we need to know is their variance, because then we can predict that variance with other things or make it a predictor of other things. Said the same way, we don't estimate factor scores. We do SEM. Same idea. So here's a summary of the models that we have so far. Do you want to see what this looks like in SAS then? Or do you want to keep going in this stuff? I'll let you vote. Who wants more slides? You guys like the slides? Okay, fine. I'm good with that. We'll look at the SAS eventually. So conceptually, I'm trying to explain this to you both statistically and conceptually because I want you to know what this is for. Okay, what are we doing here? What we are doing is handling dependency. Remember, handle is the word that people use when they don't know what they're talking about. You'll read this in results sections or book chapters. Oh, well, MLM handles missing data. It handles dependency, it just handles it. How? It handles it, it's fine. So this is how it handles it. Dependency is correlation, right? In longitudinal data, there is frequently more than one type of correlation present because occasions come from the same person. So there are 3 kinds, there's probably more, but these are sort of the primary ones, that we worry about and try to build a model to account for. Mean differences across persons is one type of dependency. Some people walk in the door better than others, and so we have to account for that. That's what a random intercept is for. We allow a main effect of persons as constant mean differences. The next one is differences in the effect of time-varying predictors across people. Time is one of them. If somebody grows more than other people, that is going to introduce another kind of dependency. The random intercept kind of dependency is constant. It's the same correlation all the way across time. Time-related slope differences is non-constant. It's going to depend on what the value for time is. Analogously, anything that's measured over time, you can have differences in its effect across people. So if I measure your stress every day of the week and your health every day of the week, some people are more reactive to stress. If I were to plot each person's slope between stress on the x-axis and health on the y-axis, some people's slopes would be stronger than others. That would introduce a type of dependency that's specific to one's value of stress. And then last but not least, there's just the fact that occasions that are closer together in time tend to be more related. And that's what the rest of the alternative covariance structure models are for. And that type of dependency we typically try to address in the R matrix at level 1, after including whatever random effects we need at level 2. So here's the way it works then. Once upon a time, starting at the left here, there was E variance. All the variance in one pile. First thing that we did in estimating an empty means random intercept only model is to take that E variance and split it into two kinds. We're not explaining, we're partitioning. The sum of these put back together again is basically E. Depending on your exact estimator, it can wiggle a bit, but conceptually, you can say that. Both of these things are considered error. They're error of different kinds. So have you guys had G-theory classes? This sounding familiar? Error for different reasons? G-theory is a random intercept model. Don't tell anyone. It's the same. It has more than one random intercept for different kinds. So at this point, we've just split variance. The next thing we did is put in a fixed effect of time. A fixed effect really does explain variance. So if I have like a little Pac-Man hand, you guys at home can't see, but I'm eating my level 1 residual variance. So picture this with a big chunk out of it, right, that time took. The next thing we did is add a random time slope. And that turns it into 3 kinds of error. Now, where did this come from? This is the tricky part. This one, excuse me, random linear time slope. It actually came from this E pile. It came out of the residual. That's where it came from. Think of it this way. Why would we have E variance? It's the variance around the line. Well, if some people need a different line, we can soak up some of that E variance and put it over here instead. Part of the reason that you were off your line is that the line that was fit for you, that everybody shared, is not good enough. You need your own. If I give you your own, some of that error that we have called time error is actually person error. It's person slope error. So now we have 3 kinds of error variability. That is to say, we have not explained anything by adding random time. We have repartitioned. And I call these error terms because we don't know why people need their own slopes. It's still error in that sense. Our job is to explain it. But demonstrating that there are these differences to be explained is a logical precursor to explaining them. So this is the point where we're at. We have within person E variance at level 1. Why are you off your line today? I gave you your own line. Isn't that enough? And then there's 2 distinct kinds of between person variance. Intercept variance, why did you start out higher than everybody else? Slope variance, why are you changing more than everybody else? 2 different kinds of person variance, 2 different kinds of dependency. So how these models handle dependency is they put a pile of variance in that represents the dependency. Now what's left, this E variance, is supposed to be constant variance across time, unrelated across occasions. The only reason why it would have been related is now in level 2, intercept differences and slope differences. two kinds of dependency. There was a question, yeah, do that for a second, after class about intraclass correlation and when you calculate it and when you don't. So conventionally, intraclass correlation is only calculated from an empty model. So at this first step, we figure out how much is level 2 relative to total. So let me do a paint example here. Let's say that here's my giant pile of variance, and I find out that my ICC is 0.5. There, that's my best attempt to equal halves. I'm sorry, I'm not an artist. So let's say that this is level 2, which is between, that's a B, and this is level 1, within. Okay. So if I add time to the model, which half is going to be reduced by time as a fixed effect? Level 1, okay? So let's say that time explained half of this variance. So that's going to be my half. Okay, this is gone. Okay, so the unconditional original ICC is 50.5, 50-50 split here. The conditional ICC, now if we take this here and we look at the relative balance, now it's 0.75 because of what's left. This piece of the pie here, 75% of it is level 2 and 25% of it is level 1. That conditional ICC is not frequently reported. You can, there's nothing stopping you. But the problem is that if I told you the conditional ICC is 0.75, you don't know if it's because there was just 75% between variance in the first place, or because your level 1 model was relatively better at the variance being explained. So it's both. The conditional model ICC is a function of how much variance of each kind you had and how much variance your model was able to explain.
Ask a question. I'm just
Yeah.
a little confused. Is the second ICC 66% or 75%? Because the remaining portion is 75?
Thank you, you're right. The mathematician is correct, yes. Yes, sorry, I was trying to do math in my head on the fly again. I should stop that. But yes, the initial ICC was 0.5. Of this variance that's left, 2/3 of it. There. That good? That's my repeating sign. So yes. But the point is, like, the partitions are what's left, and what's left is dependent on the predictors that are in your model. So the conditional ICCs are typically not reported. The exception is when you have this, all level 1 within. If you have a model, an empty model, where there's no level 2 variance whatsoever, the random intercept variance is estimated at 0. You put in a predictor, eat away some of the variance, the random intercept variance is going to come back. Because, let me go back to that slide. The random intercept variance is going to come back because the model tries to estimate what the true variance is by taking the observed variance and reducing it by a function of the residual variance. So if you reduce this residual variance, there's going to be more variance here than there was before. So it comes back. So in situations in which you start out with a model where the ICC is 0, you can't even estimate it. Some people would recommend putting in time so that you can reduce the correction factor and get the ICC that would be after controlling for time. So in the UPOX book, for instance, he recommends doing this. I don't recommend it because to me it seems arbitrary just to put in linear time as opposed to whatever other fixed effects of time you need. But then in that case, you might say you're reporting a time conditional ICC, something like that. Okay. Questions, thoughts? Okay, I'll quit drawing. So we're back at slide 25 then. So where we're at right now then is 3 types of variability to be explained. Why are you off your line today? That's E-variance. The only type of predictor that can explain that is a time varying predictor. There are 2 kinds of between variability, in intercept and in time slope. The only type of predictor that can explain these is between person, time constant predictors, or what's known as time invariant. So our job then, once we figure out how many different types of random effects we have that is related to time, is to then go about adding predictors of each type to reduce each type of variance. But we can't do that until we know how many different types of person dependency we have. And so we have handled it by introducing these terms that explicitly predict that dependency. Okay. So has anyone had any classes in econometrics? No? Okay, well then I don't have to belabor the next point. Random effects aren't the only game in town. You can also do fixed effects instead. And in certain fields, like econometrics, this is way more common. So instead of putting in a random intercept, if I wanted to control for the fact that some people start out higher than others or have higher means than others, I could put in person ID as a categorical predictor. So if I had 50 people, I put in 49 dummy codes. Crazy, but you could do it, right? That's the main effect of person. That is a fixed effect instead. That would do the same thing as adding 1 random intercept variance. U, 0, is a random effect of person. I could replace that with 49 dummy codes, which would be the fixed effects of person. Same thing with the time slope dependency, the other source of dependency. I can have 1 random time slope variance, or I can put in 49 person ID by time interactions. So why do it one way versus the other? Both of these control for dependency. Both of these methods handle dependency. But they dictate then what you can then do next. If you want to know why it is that people start out differently or change differently, person has to be a random effect, has to be random effects models, because these are sources of variance that predictors can then explain. So these models allow you to first test if there is that kind of variability, and then what predicts it, quantification and then prediction. In contrast, if I had no interest in finding out why it is some people are higher than others, I just need to control for it, fixed effects could do that too. But if I have 49 dummy codes in the model and I want to know why men and women are different, can't answer that question. The 49 dummy codes already explained everything away. Now, an ID variable is not an explanation, but from a removing the dependency point of view, it's sufficient. So the other side of this is fixed effects are more useful when you care about the specific entities that the fixed effects refer to. So I can give you a couple of real-world examples of this. I have a paper with some colleagues, a former grad student and a colleague at Kansas, who was interested in looking at N of 1 like treatment studies, basically where you have very few people but you measure them for a really long time. And if you're interested in why Bob changed differently than Susan, like if you're the therapist and you're going to have to treat these people and you want to have like the patient's treatment history, You don't care about what makes Bob different than Susan. You just need to know about what's going on with Bob, what's going on with Susan, and make decisions, right? That's when fixed effects, because that's exactly what it tells you. Another example, my husband 2 years ago became a little local celebrity at KU because he has a hobby of building statistical models to predict sports outcomes, football and basketball. Of course, basketball very big at KU. And so he built this algorithm to try and figure out who's going to win the NCAA tournament. And he got it right. It was Gazaniga, or whatever the hell that place is called. And so all like the local papers wanted to interview him. I got to be a source for one of the interviews, you know. But that's a perfect example of when you care about fixed effects. So he built this multivariate model predicting points based on which team was home, which time was away, on like the whole set of the outcomes for the year. And then he had specific predictions for specific pairs. So she's like, yeah, it's like, yeah, you can't go to Vegas with this. It's not that good of an algorithm, but it did pick Gazaniga. So if you want to know what is it that makes some teams more likely to win the playoffs, random effects. If you want to know if KU is going to get beaten by Gazaniga, it's fixed effects. So two different ways of getting to the same idea of controlling for dependency, handling dependency, but only random effects then allows you to ask questions about why the dependency is there in the first place. With me? Okay. All right. So effect size. We talked about effect size with respect to fixed effects, how much variance is explained. You can also take your test statistics for the fixed effects, your T's and F's, and convert them into D's and R's or G's or whatever effect size measure you want. But effect size for random effects is something that is frequently misunderstood. So I'm presenting you with two ways of doing this that other people have come up with, but that I like. So we can't talk about R square when it comes to random effects. It's not appropriate. Random effects make new piles. When we partition this level 1 residual variance into level 2 slope variance, it's not explaining it, it's reallocating it. So we can't talk about variance explained in any way, shape, or form when you add random effects. Because what you're doing is changing the number of variances that there are to be explained. You're going from a 2-pile model to a 3-pile model. So what do you do instead? Well, likelihood ratio tests are used to assess whether or not a variance source is significant. So we're going to add a random slope, compare the model to the version that had only a fixed slope, see if it improves in fit. Easy peasy. But the fact that the random slope variance is significant just tells you that it's bigger than 0. It doesn't really give you a sense of what that means. So for instance, the example we're working with, example 5, the fixed slope estimate is 1.7. So the outcome goes up by 1.7 for every unit time. Cool. Random slope variance is 0.91. Okay, what's that? What do I do with that? Well, I can tell you if it's bigger than 0, but in terms of trying to explain it back to somebody what that term means, that's where effect size comes in. It's tricky. So there's 2 ways that I would recommend doing this. Intraclass correlation does not apply here because slopes and intercepts are correlated, so you can't just like add them together somehow. So the 2 ways of conveying effect size when you have a random effect, such as an intercept or such as a slope, is a random effects confidence interval or a random effect index of reliability. And these are things you have not seen before. Everyone knows what a confidence interval is, but this is a different kind. And reviewers will be confused. It will be up to you to very clearly explain what kind this is. So here's how it works. Random effects confidence interval is made as such. It's the fixed effect plus or minus, if you want a 95% confidence interval, 1.96 times the square root of the random variance term that goes with it. So, quick quiz here, statisticians. What's the square root of a variance? Yeah, got that one, right? Standard deviation. So this is basically saying, all right, the fixed effect is what happens on average. If I go out like 2 standard deviations on either side, that explains what the range of the effect is predicted to look like in my sample. So putting these numbers in for this example, fixed slope of 1.7 plus or minus 1.96 times the square root of the random slope variance. That gives me this interval, minus 0.15 to 3.59. So what that means then, that's an effect size of sorts for the slopes across people. On average, the slope is 1.7. But this model is telling me that across 95% of my sample, the individual slopes are predicted to range from minus 0.15 to 3.6.
But if you have like only have like one people effect, then this index will carry me.
If I only have what? I'm sorry?
If you have one people in your
One person?
no, sorry, 5 people in your data.
If I have 5 people
Yeah.
measured over time?
Yeah.
If I have 5 people measured over time, I probably wouldn't be using random effects. That's a case where I would put in 4 dummy codes for my 5 people and call it good. Because if, in terms of prediction, you have no power to predict why those 5 people differ from each other. So you probably shouldn't even try. Whatever variance you'd estimate is probably going to be way off anyway. So this applies in samples in which you've decided to go with random effects and you have at least enough people for that to be plausible. But here's where the confusion comes in. And I've had this happen in papers before. Some reviewers will look at this confidence interval, it overlaps 0. And they're like, hey, your slope's not significant. Okay, now what? Dear reviewer 3. It's always reviewer 3 that thinks they know methods and someone else thought they did, so they got asked to review your paper and you're like, first up, dear reviewer 3. We apologize that we were not sufficiently clear in describing the confidence intervals. That's always step 1. It is your fault if they don't understand. As we have hopefully made more clear now on page 27, what do I say? Because they're wrong, but I got to clear up the confusion. Is my slope significant? That's this. My slope, got to be more specific. The fixed slope of 1.7, it was significant in the example that we did. It's significantly different than 0. And I could ask for a confidence interval around that slope estimate. It's the slope estimate, 2 standard errors on either side of it, right? That's the confidence interval they thought they're looking at. That describes the precision of that number as the mean of the sample. How sure are you that this is the mean slope? Well, my confidence interval didn't overlap 0, so it's not 0. That's all I can say. What this number refers to is the people. On average, the slope is 1.7. People grow on average significantly. However, at the individual level, the model is predicted that there's variance around this slope such that some people actually are predicted to go down. Some people grow a lot more. That's why it overlaps 0. Yes?
So it sounds like it's more like just an interval.
It's an interval.
Yeah.
Yeah.
Not like confidence interval.
Well, it's yeah, maybe calling it interval would be better. I'm just following, this comes from Snyder and Bosker, so I'm following their words. But yeah, whatever words you can use to make this better would be great. What I typically do is give them the formula, say this is my formula, and then I try to phrase it as, you know, like on average, yeah, people are growing, but we also found significant variability in growth such that not everybody was actually predicted to improve. And the reason that I like this is that for two reasons. Number one, it puts it in the metric of the original variable. So if I know what my outcome is, I know what a 3-point difference means, and I know what no change means. So it puts it back in the same metric that this 1.7 is, which is helpful. The other reason that I like it is because then you can talk about how to talk about your variability. So in this case, given this pattern, I would probably still stick with individual differences in growth. If I had a pattern where this was close to 0, and so this was more evenly spread from negative to positive, I can't say individual differences in growth. I'd have to say individual differences in change, because some people are growing and some people are declining. Likewise, if this was negative and most of the interval was on the negative side, individual differences in decline. This matters when you start fitting models where you're trying to predict the random slope, or in particular when the random slope is a predictor. And you have to know if a high value means that they are going down less or they're going up more. You follow me? Because these things are all relative to the fixed effect. So these are all deviations. So if I picture, like, if I rank order my random slope effects, the top of that distribution, it could still be a negative number if the whole distribution is negative. And being at the top means I don't decline as much as everybody else. In contrast, if most of the interval is on the positive side, then me being at the top means I grow more than everybody else. Two different things. So these can help you figure out where you're at, relatively speaking, in talking about the average and what's going on around it. The other, yeah, question? Sure.
So I'm also confused about the confidence interval. If we only look at the fixed effect, the way we interpret the confidence interval is that we obtain like a different sample. So if I have 100 people in the population, and the next time I got another 100 people from the population. So that's how we explain the fixed effect, like when we set up the confidence intervals around fixed effect. But for the random effect, now you build up the random effect confidence interval in this way. It looks like from the sampling framework, I kind of want to.
You want to say population?
Not population. I was wondering if we are still talking about the same 100 people, but we sample them like from different time, but we're still focusing on that 100 people. We cannot make inference about another 100 people. So I'm wondering, so for the random effect confidence interval, so to what extent can we explain, like, I don't know, like generalize it?
The reasonable people may disagree with me, but to me, there's no information in this interval about the precision of either of these two numbers.
Yeah, well, I think my question is, for the random effect confidence interval, can we only talk about those particular 100 people?
I think yes.
Or we can generalize to another 100
I
people?
don't think so.
Okay.
Because you would have to know sort of like what you described, right? If I did the study again, then you have a standard error that goes with this number, and you have a standard error that goes with the random intercept variance number 2. So you'd have to talk about both of those, and then from those other versions of these two numbers that the standard error implies, then you'd have different intervals.
Yeah.
So I can see where you're going, and I think maybe no one would yell at you if you thought of it that way, that you could talk about another 100 people. The world that I have lived in is that the samples are so much convenient samples that I feel really squishy about talking about a population. It's like, yeah, no, these are the 20 people I could get. Let's just hope they're representative of something, but it was really hard to get them and it was expensive, and so these are 20 people. I just personally tend to shy away from inference language that talks about populations and all. But I do think if you think about that from that perspective, that the interval is a consequence of these two things, then I think you could say reasonably that it does apply to, like if you did this again, what would the interval be? But there's no interval of this interval. I think that's what I'm trying to say. I'm saying it badly. I must have had too much coffee today. I'm on the other side of the coffee curve, right? Where you start coming back down and you're worse than you were before. But yeah, you'd have to come up with the interval of the interval to talk about how the interval changes or would vary across samples. There. That's deep. Okay. So the other way, this is from a paper by John Willett. It was on your reading list for the first week. He came up with these reliability coefficients. There's also this, I want to say, for intercept reliability in the Radenbush and Bright text. So these are relatively well known. I don't see them reported a lot. Where these can be useful is power analysis. Because when you're trying to anticipate values for the effects in your model to do a power analysis for sample planning, it's really hard to pull a number out of the air for how much random variance you're going to have. Because it's scale dependent, it's to some extent dependent on your sample sizes. And so these numbers can help you do that. And so that's a situation in which I've used these before. But I have a typo. Darn it. Where's my typo? What's wrong with this equation? See, it's a learning opportunity when I screw up. I'll pretend I did it on purpose. Yeah, this intercept is the 0. This is a copy-paste error. I'm going to fix that live here. Let me get this down. There it is. That should be 0, not 1. 1 is the slope variance, not the... I have the legend correct over here. So there's that. So yes. And why isn't my I bolded? I don't know. Apparently it doesn't want it to be an I. So yes. So these formulas kind of look like classical test theory. True over true plus some kind of relationship to error, right? So that's what I mean by reliability. It's like signal to noise. In this case, the residual variance has to be corrected for the level 1 sample size. And in the case of the slope, this extra term in the denominator right here is the variance of the level 1 predictor, because this is scaled relative to what the scale of the predictor is. So you have to correct for that in terms of the variance components. So what I end up doing in power analysis is coming up with reasonable values for what I think these are. Like I may have an intercept reliability of 0.8. That's usually pretty easy to get. Slope reliability is harder. Lower values would typically be expected for that, but if I said maybe 0.7, if I plug those in and work backwards, now I can guess what reasonable values would be for my random effect variances. So to do power analyses, all you need to know is what your ICC is from an empty model, because that gives you the relative balance of E and U0 variance. And then once you have the E variance, then you can come up with an estimate for slope reliability that gives you these things. So that is useful for that purpose. Like I said, I don't typically see it reported. Intercept reliability more often than slope reliability. But that's how I would convey effect size. All right. Questions? Okay, so on your homework, I'm going to ask you to do both of these types of calculations. You'll get a chance to practice. All right, want to see some matrices? Yeah! This is the first group that I've ever gotten such a response. Normally people are like, no, I'm good. Just go back to drawing. Can we talk about piles again? I don't want the matrices. So, conceptual. Now, why do I need to tell you about matrices? Because this. Reminder here, what's the point? So we've talked about modeling dependency. We've talked about establishing what types of variability exist in your outcomes, for which you then need predictors. But what's going on under the hood is that we're still trying to match the pattern of variance and covariance of your outcome across time. So random intercept only is this compound symmetry. Unstructured is everything gets to be what it wants. That's the answer key, which is possible in balanced data only. We're trying to come up with some sort of pattern that matches unstructured but does so more simply, more parsimoniously. So random effects models, random intercept and slope models give you some pattern that's in the middle here. So let me show you what the pattern is. It's harder to see than with like the autoregressive model or the Topolets, where the pattern is very easy. In random slope models, so we'll go back here, slide 30. This is the variance structure that we're talking about right now. At level 2, we have random intercept variance in 1,1, random time slope variance in 2,2, and a covariance. This is the type equals UN forever, endeavor, amen on the random line. What that means is that this G matrix gets to be whatever it wants. It makes no sense whatsoever to say that the intercept variance has to be the same number as the slope variance or something like that. It makes no sense not to have a covariance here, given that the U's come from the same person. The U's are dependent. So we put a covariance in. The covariance shows up in the analysis. It doesn't show up in the scalar equations, but when we do a likelihood ratio test to see whether or not the slope variance is significant, it's actually 2 degrees of freedom, not 1, because we're counting the covariance as the thing we added also. The level 1 matrix then, your R matrix, this is what's controlled by repeated. This we actually could make choices about. So this structure right here is called variance components. It's the linear regression model. Ease of constant variance, independent across people, independent across time is what's shown here. So after pulling out individual differences in intercept, after pulling out individual differences in change, this model says the E's have nothing to do with each other. That's testable. So if we have a lot of observations, the G matrix with 3 things in it rather, may not be sufficient. So we could go back and add, say, an AR1 pattern to these E's. It may be that even after controlling for individual differences in change, occasions that are closer together are more related. That's cool. We can make this pattern whatever we want. But this is sort of the most simplistic version where there is no pattern. There's no correlation whatsoever of the E's. So what does this model predict the variance and covariance matrix to look like? It's hard to show in one matrix, but I can show you what the pieces of it look like. So there's a derivation in chapter 5. If you try to figure out what the model implied variance is at any occasion, it works out to be the last line here. Since we're running out of time, I won't go through it, but I know you guys can all do this. Now note the things at the beginning and the end. That's what we get when we have a random intercept only model. The variance at each occasion is partly due to U0 variance at level 2, E variance at level 1. The part that's in blue here is the extra part that got added to the prediction because we have a random linear time slope. And note what it has, time squared. So right off the bat, we know that this model predicts that the variance changes quadratically over time. U-shape. There's going to be some point at which it's at a minimum, and it's going to go up in a curve on either side of that. Also factoring in is twice that particular occasion and the covariance between the intercept and the slope. So the covariance factors in here too. Likewise, covariance between any 2 occasions derives into this. The front part, the random intercept variance, was there when we just had a random intercept. By adding the random linear time slope variance, we pick up extra sources of covariance due to the covariance between the intercept and slope and the random slope variance. So in order to say what is the variance at each occasion, what is the covariance between occasions, we have to know which two occasions we're talking about. So here's what it looks like when you put it into matrices. So this is what it looks like for one person. Y sub I is the occasions for one person. X is the design matrix that holds the values of the predictors that have fixed effects. Gamma is the fixed effects. Z is the matrix that holds the predictors with random effects. So now we're adding this extra column here for time. Because we added the extra column for time, the U matrix here has an extra random slope for each person, and we still have 4 E's. So we put it together then like that. So that's a summary that was on the previous 2 pages. Now this whole MLM handles missing data, it handles unbalanced data. Here's how it does that. So this is what the model says the pattern looks like for 2 people. And actually the software estimates one ginormous matrix that has everything in it. This is what it would look like for 2. Start off with Z. Each person gets their own 2 columns. So let's say the first person had their time occasions complete and balanced. The next person had 4 occasions, but they came in off cycle. Their prediction comes, the same G matrix goes into the prediction for each person. That is, we assume everybody gets the same random intercept variance, everybody gets the same random slope variance, everybody gets the same covariance. Here's Z sideways to make the math work. Right now, everybody's getting the same R matrix. So the final product of what each person's V looks like is going to depend on which time observations go in. It's custom. Each person gets a custom V matrix based on which times they have. That's how we can do this even with unbalanced data. We're not requiring that everybody come back to the same matrix that's going to describe everybody. Like unstructured is one matrix that everybody has to share. They don't have to share. Here's how it handles missing data. Let's say the second person here has unbalanced occasions and they didn't come to one of them. No biggie. Their custom V matrix is going to be 3 by 3 instead of 4 by 4. Last thing I want to point out, and then I'll stop talking. Do you see the zeros in the off squares here? So this pattern is called block diagonal, which is like stuff, stuff, and then patterns of zeros in the off. Do you know why we have zeros in the off diagonals? Off blocks, can I say off blocks? Off chunks. Does this model say that people are dependent? No, people are independent. That's why. So this is saying that there's no reason why the random effects from these 2 people are related. But what if they were? What if these people came from the same classroom? Then we'd have to put something here in these off chunks that would allow a correlation between the U's of different people from the same place. So the V matrix would grow so that it would have whatever pattern corresponds to the type of dependency in the sample. So that's how it works. Custom V matrices for each person. The downside, because not everybody shares one covariance matrix, you don't have any way of testing absolute fit. You don't know what the right answer is because there isn't one. Anytime you can't summarize the right answer with some kind of matrix, you can't have absolute fit. What do you think? Cool stuff, huh? Yeah. Questions? All right, then we'll talk about estimation next time, and we'll do the rest of this SAS example too. All right. Well, good luck with comps, babies, visas, everything else. And we'll see you Thursday. Office hours start now if anybody wants to talk to me.